Today we are going to discuss how to perform integration using Monte Carlo methods. Monte Carlo method sizinaraga integration kamaina perform tawdagi habido adugi idea dunika. So as we discussed last time, what are Monte Carlo methods or Monte Carlo simulation? Monte Carlo simulation nadaga Monte Carlo method habisi kaina. Monte Carlo simulation is a method of estimating the value of an unknown quantity using the principles of inferential statistics. Habidi data dagi akoina infer tawba yaba ko data dagi akoina kari infer tawba yage habido adagi process ni ko inferential statistics habido how we can make predictions from data. So Monte Carlo simulation is a method of estimating the value of an unknown quantity using the principles of inferential statistics. Monte Carlo methods or Monte Carlo experiments are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. The underlying concept is to use randomness to solve problems that might be deterministic in principle. Monte Carlo methods are mainly used in three problem classes: optimization, numerical integration, and generating draws from a probability distribution. Today we are going to discuss how Monte Carlo methods are used to perform numerical integration. Last time we discussed how we can use Monte Carlo method to estimate the value of y. Last time discussed Today we are going to discuss how we can use the Monte Carlo method to estimate the value of an integral. So, one of the major numerical techniques developed in the last half century for evaluating multidimensional integrals or solving integral equations is the Monte Carlo method. The basic idea of this method is to select points in the region enclosed by the boundary and then take the weighted data as the estimated value of the integral. Early Monte Carlo simulations go back to the 1950s when the first computers became available. The Monte Carlo method integration now let us discuss that. So the idea of Monte Carlo integration of this integral how do you know integration of fx dx from the limit a to b is to use the mean value theorem from calculus. And what does the mean value theorem state? The mean value theorem states that the integral f of x dx from a to b equals the length of the integration domain. And what is the length of the integration domain here? The length of the integration domain here is b minus a. So the integral this is equal to the length of the integration domain times multiplied by the average value of f in the domain a to b. Mean value theorem integration. If you want to calculate the value of this integral, what do? We find the length of the domain, the length of the integration domain. The length of the integration domain is nothing but upper limit minus lower limit, that is b minus a. Then we multiply this length by the average value of this function in this domain times the average value of the function in this domain a to b. And the average value can be computed by sampling f at a set of random points inside the domain and take the mean of the function values. Monte Carlo method. So the average value the average value can be computed by sampling f at a set of random points inside the domain and take the mean of the function values. In higher dimensions, an integral is estimated as the area or volume of the domain times the average value. And again, one can evaluate the integrand at a set of random points in the domain and compute the mean values of those evaluations. One dimension integral mean value theorem length of the integration domain, which is upper limit minus lower limit multiplied by the average value inside this sorry, the average value of f of x in this domain. Two-dimensional integral oregana sige length ki mahuta the area of the domain multiplied by the average value of the function in the domain. Three-dimensional integration oregana the sige length ki mahuta the volume of the domain multiplied by the average value of the function in the three-dimensional domain. Aduni ko. So we'll come to that. Sampling and integration ko. Let us first use a simple example to illustrate how a basic Monte Carlo scheme works. If we want to find the numerical value of the integral, see the numerical value of the integral, s this integral is s, that is integral from a to b f of x dx. We can proceed as follows. Steps follow first, the average value of the function in the interval a to b is defined by the average value, expectation of f. The average value of f is equal to 1 by b minus a, integration a to b f of x dx. This means b minus a multiplied by average value is equal to the value of this integral. Sini ko hojik discuss togiba mean value theorem haja, this mean value theorem. Sigi integration se kari mane heba length siga average value of f multiplied to mane heba. Natra simang ni ko khone sifang ija. So this integration is nothing but the length of the domain multiplied by the average value of the function in this domain a to b. Now, how do we calculate the average value of f in the domain? To calculate the average value of f, what do? We divide the region a to b evenly into m slices. Instead of m, let us say n has mg and n on top of this would be x. Instead of xm, it should be xn. This would be n. Okay. So to calculate f, average value of f, what do? We divide the region, that is a to b, evenly into n of slices with x0. x0 is the starting point and xn is the end point. So x0 is the starting point, is the lower limit, xn is the upper limit. Aduna a to b haribo region g, what do? We divide a to b haribo region g line g when n number of slices that can divide. We divide the line a to b into n number of slices. In the limit, the width of the slice approaches 0. When n is very large, the width of each slide will approach 0. And in the limit, the width of the slice approaches 0. The value of this average will be exact. The value of expectation of f will be exact, but that is computationally expensive. If we want to find in the limit the width of the slices approaches 0, width of the slice 0 the approach it will approach 0 when n is very large, and when n tends to infinity, very large number of n. And so when n tends to infinity, we have to calculate the value of f at each of these n points. So when the number of points is very large, it becomes computationally expensive. And the width of the slice approach 0 is approximation on a. The integral can be approximated as integration from a to b f of x dx equal to b minus a by n. b minus a by n. This is the width of each slice. b minus a divided by n the width of the slice. So b minus a divided by n multiplied by integration, summation of the value of the function calculated at each point. x1, x2, x3, x4, x5, and so on. The value of f is calculated at this n number of points. x1 dagina xn power plus another term which is of second order in h. What is h? H is the width of the slice. So the integral can be approximated in this form. This is equivalent to sampling from a set of points. This is equivalent This is equivalent to sampling from a set of points x1, x2, xn in the region A to B with an equal weight. In this case, each weight is equal to 1 at this point. We can, on the other hand, select xi with I equal to 1, 2, 3, and 1 from n from a uniform random number generator in the region A to B to accomplish the same goal. Okay. So let me repeat it. To calculate the average value of f, we divide the region A to B into evenly into n number of slices. We divide this region into n number of slices, each of equal length, and the length of each slice is given by b minus a divided by n, with x naught as the lower limit and xn as the upper limit. In the limit, the width of the slices approaches the width of each slice approaches 0. The value of the average is exact, but that is computationally expensive. The integral can be approximated as is given by this. This integral is this plus higher order terms. Higher order terms, which is equivalent to sampling from a set of points x1, x2, xn in the region A to B with an equal weight. In this case, 1 at each point. This is what do we do? We calculate the value of the function at those points x1, x2, x3, x4, and so on till xn. The value of the function at all those points then we divide by n, and then we multiply by b minus a. So I know what we are having. So we can, on the other hand, select xi with I from 1 to n from a uniform random number generator in the region A to B to accomplish the same goal. Aduna sigi A to B region evenly divided into n slices. The working mahota, we can select n number of random points. We can select xi with from a uniform random number generator in the region A to B. A to B region uniform random number generator random number mayam generate to xi mayam to accomplish the same goal. If n is very large, we would expect xi to be a set of numbers uniformly distributed in the region A to B with fluctuations proportional to 1 by root of n. Then the integral can be approximated by the average. This integral can be approximated as integration of fx dx from A to B is approximately equal to b minus a by n, summation of the value of the function at those random points. Here we have neglected the second order terms. Second order terms in neglected over here, so this is only an approximation. Here xi is a set of n points generated from a uniform random number generator in the region A to B. The possible error in the evaluation of the integral is now given by the fluctuation of the distribution xi. Okay. Let us look at one example of this. Okay. Okay. So let us look at one example. What is this? We are going to in this first example in this latest CLZ outputs in current outputs clear. All outputs clear. In this first program, in this first Python program, what are we going to do? We are going to calculate the integral of sine x from 0 to pi. integration of sin x from 0 to pi hot ko doine ba integration of sin x is 0 to pi hot ke har kadi aina masai gi mean value theorem season ga hot pada masai hai gi bodo akoina mean value theorem season ga hot kanda we can calculate the integral like this. We can calculate the integral like this. So the xi hariba pointing at this points, the points xi which lie in the range from a to b, this points xi, these points can be drawn from a uniform random number generator. This points xi can be drawn from a set of n points generated from a uniform random number generator in the region a to b. So xi myam je a degina b bo ki manung da laiba range amada aina uniform random number generator toraga number generate to number myam da sigi xi zo obi ya ka doine ba. So if we want to calculate the integral of sin x from 0 to pi, what will we do? With here a will be 0, b will be pi, so this numerator will be pi, this n will be a large number, and then 0 to pi hariba 0 to pi hariba range da we find we will generate a large number of random points inside this and this random points this random number generator should be a uniform random number generator. Using a uniform random number generator, what will we do? We will generate a number of points, a number of random points between 0 and pi, and then we will calculate the value of the function at each of these points, and then we will take their sum, then we will multiply it by this, and we will get the approximate value of this integral. So we're going to calculate the integral of sine of x. So sine of x is Python masada yaujada. First we import the numpy library. Numpy library is the sine function defined. So since we want to use the sine function, we import the numpy library as np. A0, this is the lower limit, a equal to 0, b equal to pi. So the np dot pi is pi hariba value si Python masamak to yaujade, but numpy hariba sigi numpy hariba library manung sida pi value is numpy manung defined. The value of pi is defined in the library numpy. So I can numpy si combine import np have a shorthand na np have a shortcut na numpy is represent. So we have imported numpy and we have represented it by np. So np dot pi have this will give us the constant pi which is defined in the numpy library. np dot pi had, so lower limit is 0, upper limit is pi. And how many points, random points do we want to generate in the range 0 to pi? We want to generate 1000 number of random points. So n equal to 1000. X rand variable numpy dot random. Numpy is numpy library is random module. Inside the numpy library there is a module called random module the function the function the uniform have a function. And what does this function do? This function generates a series of uniform random numbers. This function generates an array of uniform random numbers lying between a and b. A ga b ga marakta laiba uniform random number may generate and how many random numbers do we want? It is given by capital N. Capital N gives us the total number of random numbers to be generated. So np dot random dot uniform have been within bracket the arguments a, b, and n. When a dagi horaga b bhawgi range you generate n number of capital N number of uniform random numbers. So 0 dagina pi manungda you generate 1000 random numbers which are uniformly distributed. So this first 4 lines, what does it do? It generates n number of uniformly distributed random numbers. Also, how many random numbers are generated here? 1000 random numbers are generated here. This 1000 number of random numbers are stored in an array which is array moina stored which is generate torani, and that array is stored inside this variable xren. Xren hai bas da sai number mayam do array moina store tor ba layer ne xren sai da already define function number ko define tore define function func func of x func of x sigi function jina return tore it simply returns sign of x. It simply returns sign of x. Sagi f to func what instead of f we have written func. So what does it return? It returns sin x. Okay. Then we initialize the value of the integral. The initial value of the integral is 0. For I in range n, capital N, for the value of I in the range capital N. So range capital N will generate how many numbers? It will generate 1000 numbers starting from 0 to n minus 1. So for each value of I in that range, integral will be the function f, the value of the function x calculated at, the value of the function f calculated at the point xi. Xren is an array of numbers. List array has the list number mayam number mayam na same array gawe array is not list ki property khatang amu tongan ba list na different data type yaw ba array na same data type of da yaw mayam do integer na to integer na to da float na float na to da ko so this is like a list ko this is an array. So xren is an array, and how many points does it, how many elements does it contain? It contains 1000 element. Array index level. So xi. So we start with I equal to 0. Then xren 0 means this will bring this will be the first value of the array. Xren 0 haibana kari generate tawani first value. Xren 1 haigana mana kari min tawani second value. Xren 2 haigana kari min tawani third value. So xren haiba array is 1000 number of uniformly distributed random number yaure. At each of these 1000 uniformly distributed random numbers, we calculate the value of the function. The function ki value is pole adu sai kari hagi function mayam dugi summation to haidra function mayam dugi summation to haibni ko series function mayam dugi summation to wadabni. So we integral do hana initialize 0 the initialize tore then I say integral so the integral haibin the summation haibna hen phobjane integral is the sum hai sum sum. This is the sum, not the integral. So sum do never sum. Here also this is not the integral, this is the sum. Sum. Sigi sum je kaino sigi summation fx never. This is summation. Sum majana summation fx never. So first we initialize the sum to 0. Then the value of the function is calculated at each of these points x1, x2, x0, x1, x2, and then that value, the value of the function at those xi's, they are then added to sum. So what does this for loop do? So for loop, this for loop calculates this summation f of xi. Summation of f of xi is for loop calculate. Then integral to pangi what do we do? B minus a divided by n jina summation multiply to. So b minus a divided by n. So what do we do? So the answer, this answer is the integral. See, answer is an integral is never called INPEGRAL. So here integral INPEGRAL here. So what is integral? Integral is b minus a divided by n. So the float n hydroxy float n hydroxy kuna so the n j so the number any divide to matam da number any divide to matam da Python 2 the d if both of this number are integers so division j integer any divide to kanda integer matai in Python 2, but in Python 3 when we divide two integers The answer will be a floating point. So we don't need to use float in Python 3. Python 3 the float is address we can straight away use n. So integral equal to b minus a divided by n multiplied by the sum. So what is that? That is integral equal to b minus a divided by the n multiplied by the sum. So this will give us an estimate of the integral. So the integral from 0 to pi of sine x is given by the value of this integral. So let me run this cell. Run Tori. Run Tori, and we'll get the output very soon. Exact answer to 2 ni ko. Exact answer to 2 ni, and this Monte Carlo simulation we should get a number which is very close to 2. Okay, here we have obtained a number which is very close to 2. Exact answer to 2 ni siga ako na fangibas na 1.98711. If I run it again, this will generate another set of random numbers, and then I will get a slightly different answer, but that answer should be close to the exact value 2. So let me run it again. See, I get 1.96. If I run it again, see, I get 1.9797. Correct? So, I Monte Carlo method sizinaraga integration ama sumana hot bigay haibko. Okay, this is clear. Do very good. The The simple Monte Carlo quadrature used in the above program does not show any advantage. For example, the trapezoidal rule yields much higher accuracy with the same number of points. Monte Carlo method in this example, the Monte Carlo method advantage of the PDF. What are we calculating? We are calculating integration of sine x from 0 to pi. We are calculating integration sine x from 0 to pi. We can also integrate that value, that integral, using our trapezoidal rule. Trapezoidal rule solve and that gives us better answer. Trapezoidal rule accuracy. So here, the simple Monte Carlo quadrature used in the above program does not show any advantage. For example, the trapezoidal rule yields much higher accuracy with the same number of points. The reason is that the error from Monte Carlo quadrature is proportional to 1 by root of n, whereas the trapezoidal rule yields an estimated error of that error is proportional to 1 by n square. So, which is much smaller for a large n. So when n is large, this when you compare this to the error in the trapezoidal rule is smaller. Aduna, for large values of n, Monte Carlo method na period Monte Carlo method na errors over here level trapezoidal rule lagi. Monte Carlo method. Why do we use the Monte Carlo method? Why don't we use the trapezoidal method? The true advantage of the Monte Carlo method comes in the evaluation of multidimensional integrals. The true advantage of the Monte Carlo method comes in the evaluation of multidimensional integrals. Let me see if I'm still recording. Okay, recording. So I repeat, the true advantage of the Monte Carlo method comes in the evaluation of multidimensional integrals. For example, if we are interested in a many-body system, such as the electrons in a neon atom. Neon atom electrons in study. Then how many electrons are there in the neon atom? Neon atom atomic number my atomic number 10. So in the neon atom we have 10 electrons. So if you want to study the 10 electrons in the neon atom, and if you want to perform some integration, the integral for the expectation value can have as many as 30 dimensions. Why 30 dimensions? Because we have 10 electrons and each of these electrons are independent, And then each of these electrons have 3 degrees of freedom. Electrons in 3 degrees of freedom, like they can either move in the x direction, y direction, or z direction. Each of these electrons, they can either move in the x direction, y direction, z direction. Electron could 3 degrees of freedom, like, and if we have 10 particles, 10 electrons, then total number of degrees of freedom will be 30. That is, the total number of dimensions will be 30. Integration we will have 30 independent variables. One-dimensional integration, two-dimensional integration. This is 30-dimensional integrations. Case Monte Carlo method advantage. So for a d-dimensional space, the Monte Carlo quadrature will still yield the same error. Monte Carlo method errors dimension it will still yield the error which is proportional to 1 by root n. The Monte Carlo method gives an error which is still proportional to 1 by root n, where n is the number of points sample. However, the trapezoidal rule has an error of delta S is proportional to 1 by n to the power 2 by d. 1 by n to the power 2 by d. Trapezoidal rule error d dimension and it is given by 1 by n to the power 2 by d. And this error becomes greater than the Monte Carlo error estimate with the same number of points if d is greater than 4. 4 dimension when the integration has more than 4 dimensions. If we are considering 4 dimension integrations with more than 4 dimensions, the Monte Carlo method errors in the pixel are never. Trapezoidal rule errors in the the point is that the Monte Carlo quadrature produces a much more reasonable estimate of a d-dimensional integral when d is very large. Dimension is Monte Carlo procedure there are some specially designed numerical quadratures. Integration performed numerical method. So there are some specially designed numerical quadratures that would work still better than Monte Carlo quadrature when d is slightly larger than 4. However, for a real many-body system, the dimensionality in an integral is 3 times n, where n is the number of particles in the system. And when n, the number of particles in the system is of order 10 or large, what do? Any other workable quadrature would perform worse than Monte Carlo quadrature. When the number of dimensions is much larger than 10, 10 the method numerical method Monte Carlo method advantages for enable. Say the n here in this particular example, in this particular line, n n is the number of particles in particular line. The n is the number of particles, whereas in the earlier case, what is n? N is the number of points inside the domain. Say that confusion instead of capital N, let me use small n. N generally. So the small n is generally confusion. Okay. Monte Carlo integration की मागे real advantage है कहना. Monte Carlo integration की real advantage है it is when we calculate multi-dimensional integrals. Multi-dimensional integral matamda मागे real advantage लाखने. Okay. Let me see if I have another example. Okay. Saigi equina sigis data. Ziki example number 1 is the equin example number 1 is the equin we estimated the value of the integral sine x sin x from 0 to pi. 0 to pi sin x की integration होती बनी exact value di 2 ni kuna Monte Carlo method sin raga polisina, and we get a number which is very close to 2. We get 1.9797 and so on. Yarba aduga sigi sida kuna second sida second da what is kari no have matam da sigi calculation je kuna hanjan repeat to. As I said, the 1,000 points Loroga, 1,000 points Loroga, 1.9 something like I get a different value, but still very close to 2. So n equal to 1,000, let us see. 1.9797. If I calculate it again, I get 1.96. If I calculate it again, I get 1.969. If I calculate it again, 2.0547958 and so on. So each time we perform this, we run this program, we get slightly different values. So if we run this program 2,000 times run the programs and see generate the number graph histogram distribution of areas calculated. So we have run this program 2,000 times. 2,000 times run tore aduga ngasai generate toreba answer mayam do adugi histogram amaye, and what do we see? 2 zigi exact value zigi maya da ko exact value zigi maya da. Most of the answers they lie in around the value 2. So let it go. 2 is the maximum number of answers. 2 is the time. Exact values no kya exact values is 2 never. Monte Carlo simulation in 2,000 times run the values different values in histogram plot tokanda maximum exact values Monte Carlo method when we increase the number of points in this range, the value we should get more and more accurate. So if I increase 1,000 points, if I increase the number of points to 10,000, I should get an answer which is more accurate than this. So let me run it now. See, I see when I increase it to 10,000, I get a number which is very close, 1.99576. To the hand. So when you increase the points, 0 and run it again, all right, we should get, theoretically, we should get more and more accurate answers. Because why? Because the error is proportional to 1 by root over n. So when n increases, the error should decrease. So already multi-dimensional integration. The Monte Carlo method is real advantage in calculating multi-dimensional integral. So then how do we calculate a multi-dimensional integral using the Monte Carlo formula? Here is the process. The general integral formula in d-dimensional space is given by I equal to this, I equal to f of x dvd, and what is x? So the x the arrow x vector this x represents a point in the d-dimensional space. So this x actually consists of x1, x2, x3 till xd. 3 dimensions already this x vector is equal to xyz. In 3 dimensions, this x vector my components into xyz or any. In 2 dimensions, this x vector will be x comma y. In d dimensions, this x vector will be x1, x2, x3 till xd. And what is d of vd? dvd is here vd is the d-dimensional volume element. So here dvd is the d-dimensional volume element. So dvd is the dvd is the dx1, dx2 multiplied till dxd. And what is this? This is equal to This is equal to the volume V. What is V? V is the volume of the domain. Say one dimension V is one dimension V is simply length of the domain V minus A. But in d-dimensional, it should be V, the volume of the domain. V divided by N, then summation of the function F calculated at those points. So in d-dimensional space, this X will have D components. So let us look at one example. Two-dimensional integral. Two-dimensional integral to the say I equal to ax integration f of xy dx dy. So the dx like record dx dy. So x goes from ax to bx, y goes from ay to by. This is the integration. So f of xy dx dy and a dx to just dx. I can put the dx here also. Say that I and a dx integration limit say ax again bx pony, y limit na ay again by pony. Using this formula, saying formula as a v kaitani, v will be bx minus ax whole into by minus ay. In 3 dimensions, so this v will be bx minus ax whole into by minus ay whole into bz minus xz. So bx minus ax, by minus ay in 2 dimensions. Then we divide by the total number of points. The total number of points is n. And what do? We find out the values, the value of the function at this n number of points, which are given by xi, yi. And then we take their sum. We have to do in general. So negative we multiply by this, and we get the integral. Example: integral of this integral 2x square plus y square. Have integral now you integrate this with respect to dx and dy, x from 0 to 2, y from 0 to 1. The exact answer is 6, and let us calculate it by using the Monte Carlo method. Monte Carlo method policy, we should get a value which is very close to 6. Zikidu, okay. So let me show you the integral again. X ki limit na 0 to 2, y ki limit na 0 to 1. So what do we do? Ax 0, bx 2, ay 0, by 1. So x ki limit na 0 to 2, y ki limit na 0 to 1. So let go. X ki limit na 0 to 2, y ki limit na 0 to 1. And what is the integrand? The integrand is 2x square plus y square. The integrand is 2x square plus y square. So that is the function which we have defined here. Define function of x and y, that is 2 multiplied by x squared plus y squared. Then what do we do? First, NG 1000 let us generate 1,000. Let us take 1,000 random numbers, random points. So what do we do? NP random uniform from AX to BX N. X key 0 dagina 2 working manungda 1,000 random points generate tawra. Atagin tawriba random number mayamdu X ran hariba array the shape tawra. Similarly, Y gisu AY dagina BY hyper range data you generate 1,000 number of random points, and then you store this array in the variable y ran. So X ran is an array containing 1,000 points lying between 0 and 2. Y rand is an array containing random points lying between 0 and 1. And how many points? 1,000. So 1,000 x values, 1,000 y values. The function is twice x square plus y square. So twice x square plus y square. The idea we use this formula. So first we will calculate this summation. So you calculate the value of f at x0, y0, the x1, y1, x2, y2. This is lower. So first, first integral integral code. This is called sum sum. So this is not integral. This is sum. SUM. This is the sum. So integral nate, this is the sum SUM, and then answer is integral to never. This is the integral. Integral. This is the integral. So this is also the integral. Integral. This is the integral. So what do we do? X ki limit, Y ki limit low, number of points 1000 low. So 1000 random values of X generate 1000 random values of Y generate. This random values of X it lie between 0 and 2 given because of this, and this 1000 random values of Y it lie between 0 and 1. So I integrate the function I integrand to define next next after that what do we do? First we calculate this summation. Sigi summation follow summation first we initialize the sum to 0. 0 then in the for I in the range 0 to n is 1000. So we calculate the value of the function at each of those xi, yi the whole x0, y0 the function whole the value do sum the tinjale x1, y1 the function do whole value do tinjale so and so on until xn, yn the function do whole adu tinjale. Correct. So the for loops this for loop it calculates this summation. The integral this integral should be equal to bx minus a whole into by minus y divided by n multiplied by the summation. So what is this? Integral equal to bx minus a multiplied by bx minus y divided by n multiplied by the summation. So this is the value of the integral. The exact value the exact value is 6, and let us see what value this program gives. So let me run it. Control enter. The value of the integral is 5.98335, very close to 6. If I run it again, I should get a different value, but still close to 6. I get another value which is close to 6. If I increase the number of random points, say 1000 again, 1 lakh I should get more accurate answer. Let me run it again. I get a value which is very close to 6. So if you increase the number of random points, the accuracy increases. This is for 2-dimensional case. Now let us look at this example. 3-dimensional case. I equal to dx, dy, dz. This function, what is the function? Y sine x plus z cos x. X ki limit na 0 to pi, y ki limit na 0 to 1, z ki limit na -1 to 1. Answer na kya tagadaba? Answer na 2 tagadaba. Correct. So x na 0. So let us write this program. So x ki limit 0 to pi. Pi have a Python must have the yaujudabanina when numpy import import numpy. Random module numpy. So in this program we always import numpy. So numpy import x ki lower limit upper limit defined y ki lower limit upper limit defined z ki lower limit upper limit defined and the number of random points. Let us start with 1000 random points. X ki lower limit amasung upper limit ki marakta we generate 1000 random points. So we generate 1000 uniformly distributed random numbers lying between ax and bx. Similarly, we generate 1000 random numbers for y lying between ay and by, and similarly we generate 1000 random numbers, uniformly distributed random numbers for z lying between az and bz. Method so this three intervals they are taken care of. Sorry here. These three intervals 0 to pi, 0 to 1, -1 to 1. And what is the integrand? The integrand is y sine x plus z cos x. Y sine x plus z cos x. So the integrand is y sine x plus z cos x. Sine x is Python masada yaujadabanina when numpy manungda defined over sine x we are using the function sine x which is defined in numpy. NumPy library which they are defined over sine x so call import numpy as np. Numpy is the np haiba shortcut sina np kauraga import tore. Whenever you want to call numpy, you simply write np dot haiga my function to call to. So np dot sin x. So this is nothing but y sin x plus z np dot cos x. So this is z cos x. So y sin x plus z cos x. This is the integrand. Y sin x plus z cos x. This is the integrand. Next, now integral. See integral higher. This is sum. This is the sum. So this integral higher sum. This is sum. This is integral. This is the sum. So this is not integral. This is the sum. And see answer. This answer is the integral. This answer is also the integral. Random numbers into generate function define integration function to define already have sum initialize already for loop sum to call so then 2 dimensions f of xi yi in 3 dimensions it will be f of xi comma yi comma zi. So here we have function x random I, y random I, z random I. And we go from I from 0 to n. And then we calculate the value of this summation. Next, in 3 dimensions, what will be this multiplying factor? So the multiplying factor will be bx minus ax whole into by minus ay whole into bz minus az. Divided by n. So here we have integral equal to bx minus ax whole into by minus ay whole into bz minus az divided by n multiplied by the sum, and then we get the integral. So let us run this and magi exact value kya tagadabno exact value 2 tagadabni. Let us see how close to 2 we get the value. We get a value which is very close to 2.025. If I increase the number of random points here, 1000 again, 1 lakh increased already, I should get a more accurate answer. Let me run it again. It's 2.020. Let me run it again. I should get a different answer, but it should be very close to 2. So this is how we use the Monte Carlo method to evaluate an integral. And then last example, this example I leave it as your homework. Someone is example 2, example 3. You simply change the limits of integration, and then you simply change the function. Function j integrand is define to define limit to change the program. The answer should be 15. So that is all for today. Let me stop the recording.